In the autumn of 1957, the American driver wanted exactly one thing: total, lazy, effortless control. The interstate highway system was freshly paved, gasoline was 29 cents a gallon, and Detroit's golden rule was simple. You put the engine in the front, you put the drive wheels in the back, and you put a solid steel lever behind the steering wheel so the human being could tell the 3-speed automatic transmission what to do. It was a mechanical handshake that had worked flawlessly for a decade. Then, the Ford Motor Company spent the equivalent of $2.5 billion modern dollars to invent a steering wheel that actively tried to destroy its own transmission. When the silk sheet was pulled off the 1958 Edsel, the public didn't look at the infamous polarizing vertical grille. They looked at the driver's seat. Sitting dead center in the middle of the steering wheel, right where the horn had lived since the dawn of the automobile, was a floating saucer of glowing green plastic. 5 mechanical push buttons arranged in a tight, planetary circle: park, reverse, neutral, drive, low. They called it Teletouch. The marketing department promised it was the dawn of the jet age. You didn't shift an Edsel, you played it like a grand piano. To the average consumer standing in a bright showroom, it looked like a triumph of 20th century futurism. To the transmission engineers buried 3 floors deep in Ford's Dearborn research labs, it looked like a ticking pipe bomb. Because to make those 5 little plastic buttons talk to a 400-pound cast-iron gearbox sitting 6 feet away, Ford's engineering team had been forced to break the most sacred rule of automotive design. Never route high-amperage electricity through a high-friction, constantly rotating joint. To understand the sheer insanity of what Ford's Special Products division attempted, you have to look at the anatomy of a standard 1950 steering column. It is essentially a heavy steel pipe. Inside that pipe sits a solid steel shaft spinning up to 450 degrees left and right, bearing the brutal, unassisted mechanical load of turning 2 2-ton tires against dry asphalt. It is a hostile, greasy, vibrating, high-torque environment. Now, imagine taking that exact same spinning steel shaft, drilling it hollow like a drinking straw, and trying to snake a bundled wiring harness of 12-volt copper conduits straight down its center. The mandate from corporate executives was absolute. The center hub containing the buttons must remain dead stationary, even while the steering wheel rim spun furiously around it like Saturn's rings. It was the mechanical equivalent of trying to keep a compass needle perfectly still while tapping it to the side of a running washing machine. The engineers knew the physics were fighting them. They knew that copper wire, subjected to thousands of continuous twisting cycles inside a narrow, grease-filled metal tube, doesn't just bend, it work hardens, it chafes, and eventually it snaps. But saying no to a flagship corporate gamble wasn't an option. So they didn't just build it. They built a system so complex it required its own mechanical translator. And that was where the nightmare truly began. To convert the gentle, millimeter-long press of a plastic drive button into the brute mechanical force required to move a heavy hydraulic transmission spool valve, you need leverage. Normally, a human arm provides that mechanical advantage through a solid steel linkage rod. But buttons don't have arms. They only have electrons. So the engineers had to invent a mechanical middleman. Down beneath the floorboards, bolted directly to the left side of the cast-iron automatic transmission, they mounted a massive, cylindrical electric servo assembly. Think of it as a robotic hand. When a driver pressed drive on the steering wheel, a 12-volt electrical signal shot down the hollow steering column, breached the firewall, and woke up this electric motor. The motor then spun a set of intricate internal reduction gears, physically rotating the transmission's external manual selector shaft into position. It was an electromechanical masterpiece, essentially a primitive fly-by-wire system built nearly half a century before the automotive industry was actually ready for it. On paper, the engineering specifications were staggering. The servo packed a heavy-duty gear reduction ratio of 60-1. It had to overcome the intense internal hydraulic pressure of a transmission spinning at 2,000 revolutions per minute. That small motor had to generate nearly 20 foot-pounds of rotational torque instantaneously. That is roughly the same amount of twisting force required to snap a standard 3/8-inch steel bolt clean in half. And it had to execute that shift in less than 8/100ths of a second, or the driver would feel a sickening, rubbery lag between gears. To prevent the system from tearing its own guts out, the engineering team designed an ingenious safeguard, an inhibitor relay bank. This was a mechanical brain composed of copper leaf switches that acted as electrical traffic cops. If a driver was cruising down Route 66 at 70 miles per hour and their child accidentally slammed a hand into the reverse button, the brain intercepted the current. It physically locked the servo circuit out, saving the transmission from detonating and scattering its planetary gears across the asphalt. When the prototype benches were fired up in the climate-controlled testing facilities of Dearborn, it felt like pure magic. The buttons clicked with the heavy, satisfying asterisk thunk of a bank vault. The servo whirred, the linkage snapped instantly into gear, and the apparatus completed tens of thousands of flawless cycles. The engineers had solved the impossible puzzle. They had taken the messy, violent mechanical reality of a Detroit gearbox and disguised it behind the effortless touch of a modern kitchen appliance. Executives drafted triumphant press releases. The engineering team breathed a collective sigh of relief, but there was a catastrophic blind spot in their testing methodology, one that no pristine laboratory bench could ever replicate. They had perfected how the Teletouch system operated in a vacuum. What they hadn't accounted for was real estate. Because when you bolt a precision, tightly sealed electric motor directly to the side of a transmission housing, you aren't just putting it under the car. You are placing a fragile piece of electrical clockwork less than 4 inches away from the roaring, 1,200-degree exhaust pipe of a 410 cubic inch V8 engine. And extreme heat does very dangerous things to copper. When you expose mid-century copper wiring to continuous, radiant heat exceeding 400 degrees Fahrenheit, a microscopic chain reaction occurs. First, the electrical resistance inside the wire spikes, meaning the 12-volt motor suddenly has to pull dangerous amounts of current just to wake up. Second, the delicate shellac and cloth insulation wrapping those wires begins to bake. It turns brittle, cracks, and eventually flakes off entirely. By placing the Teletouch servo motor right next to the exhaust crossover pipe, Ford hadn't just created an engineering flaw. They had essentially dropped a delicate mechanical Swiss watch into a deep fryer. In the real world, the results were chaotic. A driver would commute for an hour, thoroughly heat-soaking the engine bay, and then pull into a grocery store parking lot. When they came back out with their groceries and pushed the green reverse button, they were greeted with absolute silence. The baked wiring had shorted out against the hot transmission housing, popping 30-amp fuses and killing the circuit instantly. But a dead button was the best-case scenario. The worst-case scenario was crosstalk. As the wire insulation melted away inside the hollow steering column and the underfloor harness, the tightly bundled copper circuits began touching each other. A driver might push drive, but the scrambled electrical signal would route to the reverse or park circuit. The inhibitor relay, the mechanical traffic cop designed to stop this exact disaster, was often compromised by the same intense heat wave. The result was a 4,000-pound steel vehicle unexpectedly and violently trying to engage the wrong gear at speed, shuddering violently and frequently shearing the teeth right off the transmission's planetary gears. And then owners discovered a completely different, mathematically terrifying puzzle. What happens when an Edsel gets a dead battery? In a traditional car with a mechanical steering column lever, a dead battery is merely an inconvenience. You physically yank the heavy steel lever down into neutral, physically disengaging the transmission's parking pawl, and you push the car to the side of the road. But in the Teletouch-equipped Edsel, the buttons on the steering wheel only spoke electricity. Without battery juice, the transmission was permanently, physically locked in park. The car instantly transformed into an immobile, 2-ton steel paperweight that couldn't even be dragged onto a tow truck without dragging the locked rear tires across the asphalt and destroying the drivetrain. Frantic Ford dealerships were suddenly flooded with stalled, broken, and dangerously unpredictable Edsels. The service bays were manned by grizzled 1950s mechanics who understood vacuum lines, cast iron carburetors, and heavy grease. They were not aerospace electricians. When faced with an intricate 60-to-1 gear reduction electromechanical servo with a melted wiring harness, they did the only thing they could do. They ripped the entire unit out and blindly ordered a replacement, billing the corporate office for massive, bleeding warranty claims. The transmission engineers in Dearborn were forced into crisis mode. They scrambled to design emergency heat shields and frantically tried to reroute the exhaust lines to save their jet-age flagship. They firmly believed they could out-engineer the thermodynamics. But they were looking at the wrong variable entirely. The heat wasn't the only thing destroying the Teletouch system. The actual fatal flaw was a deeply ingrained human reflex, and it was about to tear the Edsel apart from the inside out. For over half a century, the automotive industry had conditioned the human nervous system with one universal survival reflex. When danger appears, you slap the center of the steering wheel. It is pure, unthinking muscle memory. A child runs into the street, a truck veers into your lane, and your right palm flies inward to slam the horn. Ford's ergonomics team had moved the horn. To make room for the Teletouch dial, they relegated the horn actuator to a thin, chrome ring tracing the outer circumference of the steering wheel rim. Now put yourself in the driver's seat of a 1958 Edsel Citation cruising through downtown Chicago. A taxicab suddenly cuts across your nose. Your brain bypasses conscious thought. Your palm slams the center hub. But instead of blaring a loud 12-volt horn, your hand physically impacts 5 mechanical push buttons with over 30 pounds of panicked force. If you were traveling above 15 miles per hour, the inhibitor relay, assuming it hadn't already been cooked by the exhaust pipe, blocked the signal. But if you were navigating a congested intersection at 12 miles per hour, the system's safety parameters assumed you were trying to park. The electric servo instantly fired. The transmission dropped from drive into reverse. The mechanical violence of an automatic transmission revering its rotational direction at 12 miles per hour is catastrophic. It is the engineering equivalent of shoving a solid steel crowbar into the spokes of a spinning motorcycle wheel. The torque converter ballooned under the sudden, immense hydraulic spike. Planetary gear sets shattered, sending hardened steel shrapnel tearing through the aluminum valve body. The rear tires locked up in a cloud of white smoke, and the car violently bucked to a halt, stranded in the middle of traffic with a completely destroyed drivetrain. And the nightmare wasn't just happening to drivers. It was happening before the cars even left the factory. On the assembly lines in Mahwah, New Jersey, and Somerville, Massachusetts, line workers were given roughly 60 seconds to install the steering column. They were used to dropping a rugged steel tube through a hole and bolting it down. Now, they were asked to carefully feed a delicate, multi-wire harness through a narrow column, making sure not to pinch the copper lines against the sharp, undeburred interior steel edges. They failed. Thousands of Edsels rolled off the production line with their Teletouch harnesses already nicked, crimped, or severed. Dealership mechanics were receiving brand new, zero-mile cars off the rail cars that physically wouldn't shift out of park. By mid-1958, the warranty department at Ford was hemorrhaging cash. The Teletouch system, designed to be the ultimate symbol of effortless luxury, had become a national punchline. For the 1959 model year, Ford quietly surrendered. The glowing green saucer vanished from the steering wheel. In its place returned the heavy, simple, unkillable steel column lever. The greatest corporate gamble in automotive history had ended in a humiliating retreat. The engineers packed up their test benches, the marketing brochures were thrown into incinerators, and the Edsel name became synonymous with colossal failure. That should have been the end of the story, a bizarre footnote in the annals of Detroit arrogance. But if you look inside the cockpit of almost any modern hypercar or electric vehicle today, you will discover something fascinating. Those desperate Ford engineers hadn't actually failed. They were just 50 years too early. When we look back at the disaster of the Teletouch system, it is easy to dismiss it as a monument to mid-century corporate hubris. But step inside a modern Ferrari, a contemporary Aston Martin, or a new electric vehicle today. What do you see? The heavy steel column shifter is dead. The mechanical linkage rod is gone. In their place are sleek, haptic push buttons, rotary dials, and steering wheel-mounted paddles that communicate purely through code. The entire global automotive industry has fully embraced shift-by-wire technology. Every time a modern driver presses a button on the dash to put a car into drive, a computer sends an electrical signal down a wire to wake up a precision actuator bolted to the side of the transmission. It is the exact, step-by-step mechanical sequence that Ford's Special Products division mapped out on their drafting tables in 1957. The difference between a modern push-button transmission and the 1958 Edsel isn't the philosophy, it is the material science. Today, those electrical signals don't travel through thick, heat-sensitive copper conduits wrapped in fragile cloth shellac. They flash through shielded, heat-resistant CAN bus networks at the speed of light. The primitive copper leaf relays have been replaced by solid-state silicon microprocessors capable of executing millions of safety calculations per second. If a modern driver accidentally hits reverse at 70 miles per hour, the car doesn't rely on a fragile mechanical switch to save itself. The computer simply denies the request. Modern engineers didn't invent a new way to drive. They just waited for computing power and thermal insulation to catch up to Ford's wild imagination. And that is the true, bittersweet legacy of the Edsel steering wheel. The engineers in Dearborn weren't foolish. They were trapped in an era where the vision of the future outpaced the physics of the present. They were trying to build the 21st century using 1950s vacuum tubes, cast iron, and raw determination. It was the engineering equivalent of trying to launch an orbital satellite using a steam engine. History has not been kind to the Ford Edsel. For generations, it has been reduced to a visual punchline, mocked by casual observers for a vertical grille that critics claimed looked like an old-fashioned horse collar. But beneath that polarizing sheet metal lived a brave, desperate, and brilliant engineering team that dared to ask a forbidden question. Why are we still mechanically tied to the machine? They pushed the boundaries of automotive design so far past the edge of mid-century reality that the machine literally melted under their own hands. But in their failure, they drew the blueprint for the cockpit of the modern automobile. So the next time you sit in a new car, rest your hands on the wheel and effortlessly tap a button to select a gear. Take a second to look down at the steering column. And remember the glowing green saucer, the 60-to-1 servo motor, and the ghosts of the 1958 Edsel.